Now let us see about the structural dynamics, what they are likely to ask us. Whatever we have studied in first year engineering mechanics, as I told you, the mechanical vibrations, free vibrations, and also to some extent forced vibrations. So we'll see for free vibrations means time period and frequency, how the questions are likely to come up to this part. Okay. Dynamics. First thing is types of motion. In engineering mechanics, in the topic dynamics, you have studied 4 types of motion. One is rectilinear motion. Rectilinear motion means it is a straight line motion. Okay. This rectilinear motion occurs if there is only a resultant force whose direction does not change. Resultant moment is 0. So the body will not rotate, it will only move forward or backward, only in a straight line path. Okay, then that motion we call it as straight line motion. I think that parts I told you, we don't have to write what it is. Then you have studied about second one is curvilinear motion. In curvilinear motion also body will not rotate because resultant moment is 0. There is only a resultant force whose direction continuously changes, let us say. Then you will get a curvilinear motion. Rectilinear motion means it's a body like this, say it moves forward, backward, that's all. Straight line motion. Curvilinear motion means the resultant force direction continuously changing, let us say. Then body will not rotate, vertical member remains vertical, it moves like this. Vertical position only it will be there, it will not rotate like this because there is no movement on the body. So such motion is called curvilinear motion. Curvilinear motion occurs when there is only one resultant force whose direction is not constant. Then third type of motion is rotation. Rotation will happen if there is only a moment. Resultant force is 0, so it will not translate. Only resultant moment is there. Because of that moment, it rotates with some acceleration, angular acceleration alpha. Okay. Then sir might have told you the relationship between angular acceleration, angular velocity and angular displacements. Say something like that. Then if at all there is a resultant force and also resultant moment, then you get a motion called plane motion. Plane motion means there is a translation plus rotation. It is nothing but translation plus rotation put together happens. It is called plane motion. Now motion of a wheel on the ground. If you take a wheel, it rotates as well as translates. It is rotating because there must be some resultant moment. It is moving because there must be some resultant force. Otherwise, if force is not there, say, it could have rotated there only. It is moving means some force must be there. So translation plus rotation put together, we call it as plane motion, happens when there is a resultant force as well as resultant moment. Now in the dynamics part, which is structural dynamics, you will study about rectilinear motion. A special case of rectilinear motion called simple harmonic motion. Simple harmonic motion is a special case of rectilinear motion where acceleration is proportional to the displacement, and acceleration always acts opposite to the direction of the displacement towards a fixed point. Such motion, such oscillating motion is a straight line motion, means rectilinear motion with variable acceleration, that we take up now. Okay, that is simple harmonic motion. CH1. It is actually a special case of rectilinear motion where acceleration is proportional to the displacement. Okay, so it is a name used to describe straight line motion of a body. Describe straight line motion of a body whose acceleration is proportional to the displacement. Proportional to the displacement from a fixed origin. From a fixed origin and is always directed towards the origin. So it is a special case of rectilinear motion with variable acceleration. Rectilinear motion with variable acceleration. Okay. Now, how to represent mathematically that SHM? So, acceleration is proportional to, that means minus omega square into x. Negative because if displacement is right side, acceleration is left side. That's why minus sign. Omega square is some constant. So, this will tell you that acceleration is proportional to the displacement. This is how it is connected. A is equal to minus omega square x. This is a mathematical statement for simple harmonic motion. Now, what is that omega? If you want to see how you want to visualize, say, if you take a stone tied to a string whose radius is r, and that stone, when you tie it to a string, you rotate it in a horizontal plane. Then if you see from top, that means when you are rotating it, you rotate with some constant angular velocity, omega. Constant angular velocity means acceleration is 0, angular acceleration is 0, only angular velocity which is constant, and it is rotating in a circular path. That circular path you will see from top only, because I am rotating like this. That means first you hang it like this, gradually you turn it this way, then you can turn it. Suddenly means it will hit our head. So you have to turn it like this. Now it moves this way. From our view, that means diametral view, if you see, you will find as if the stone is moving forward, backward like this. But if you see from top, you will see the complete circular path. That means the diametral projection of the circular motion is called simple harmonic motion. It looks like an oscillating motion. That circle, we call it as auxiliary circle. Radius of the circle is nothing but the amplitude of the vibration. Vibrations means it move up and down. So what is the amplitude? That amplitude is the radius of the circle. That circle we call it as auxiliary circle. With what angular velocity it should rotate, so that its diametral projection gives us simple harmonic motion, displacement, velocity, acceleration. That angular velocity we call it as natural circular frequency, whose diametral projection frequency we call it as simply frequency. Okay. So that's what you have studied in engineering mechanics, and also in intermediate also you might have studied that. In first year dynamics, mechanical vibrations you have studied. Then time period means how much time it takes for one complete circle. That is called time period. Then in a second, how many such oscillations can happen is called frequency. That means inverse of time period is the frequency. Okay. Now that point we will see. How this comes is this one. You will take one auxiliary circle. This circle is called auxiliary circle. This is diametral projection, let us say. This is the origin, fixed point origin, you take it as a O. Initial starting point somewhere here, let us say A. It moves with a linear velocity, let us say r omega, this is r. Angular velocity omega, constant. With constant angular velocity if it moves, it is like this. After some time, if you see, it will may take place somewhere here B, say. This is angular displacement. From here to here, time taken, suppose the displacement it has taken is, say, angular displacement is theta, whose diametral projection, if I take it like this is the x displacement of the simple harmonic motion. Then if you take the velocity v is equal to r omega, whose diametral projection, here if you take the this, if with vertical you are calculating theta, now this becomes theta. So diametral projection means r omega cos theta, this value is the Vx. Vx is r omega cos theta, like that. So that is the simple harmonic motion velocity at any point. If velocity is constant, that means tangential acceleration is 0. This is what you have studied in engineering mechanics. If v is constant, dv by dt is called tangential acceleration. Tangential acceleration is 0. Tangential acceleration is exclusively due to change in magnitude of velocity. But here direction is changing. So exclusively due to change in direction, you will get normal acceleration. Even whether velocity is constant or not, simply velocity is there. If its direction changes, you will get a normal acceleration. AN is called normal acceleration. R omega square we can take it, or V square by R, whatever way you want to, you can consider. Whose x component, how the x component will act, you see. If it is moving right side, the x component of this will act left side, an x. So you will get that point as an means x component of the acceleration, you will get sine theta. If this is the component, this is theta, let us say this is 90 minus theta, cos 90 minus theta means an sine theta, an into sine theta. So you will get v square r omega square sine theta minus, you have to write that x displacement. If you want to calculate this, the acceleration in x direction, then velocity in x direction, r omega cos theta, then displacement x, you will get r sine theta, like this. X, Vx, Ax are the diametral projections of the particle displacement, diametral projections of the curved path. So this will give, that's how the omega is defined. If you take an auxiliary circle whose radius is the amplitude of vibration, with what acceleration you have to rotate it, so that with what angular velocity you have to rotate it, so that whose diametral projection gives you displacement, velocity, acceleration of the SHM. That omega we call it as natural circular frequency. Okay. So this omega we call it as R is amplitude of vibration. This omega we call it as natural circular frequency. Then time period, if you want, for one complete circle, if it has to make, what is the time period? Time taken for complete circle. That means what is the total angular displacement? This theta is like this, it comes and comes back to this position. In the process, it will go forward, backward, come back. That is one complete cycle. For the 2 pi is the displacement, velocity is the omega. So displacement by velocity, you will get the time. So 2 pi is the displacement, angular displacement by velocity. This is angular displacement by angular velocity. What you get is the time period. So in one frequency means that f, we call it as, this is called cyclic frequency. 1 by time period is called cyclic frequency. Omega is called natural circular frequency. Okay, cyclic frequency we take it as 1 by t, that means omega by 2 pi. So this is what you have studied in your first year engineering mechanics. Sir also might have told you about these fundamentals. I am just revising what we have studied and where we have to stop. Okay. Next, second point is free vibrations without damping. This about auxiliary circle, etc. If at all there is free vibrations are there, in the examination, free vibrations without damping only can be given, because in your 30 seconds without calculator you can do only that much. Okay. Once you come back for mains, then we will see the long questions also. Forced vibrations also we will discuss there. Second concept is free vibrations without damping. Only springs you have studied. This is what you have studied. This will replace it with a structure. This is some W, let us say. Stiffness of the spring is K. Time period of vibration, T stands for again time period of vibration. You will get it as 2 pi by omega. That omega value will get it as 2 pi into W by kg. So this you will have to remember, W by k into g into 2 pi. Then frequency, F is equal to cyclic frequency. 1 by t, reverse of that, omega by 2 pi. So 1 by 2 pi into square root of kg by W. W is the weight, W by g will become mass, or k by m also we can write. 1 by 2 pi into square root of k by m. In One paper, last year prelims, only this they have asked. This also this one, 2 pi square root of m by k. In this form they asked. So whatever way, W by G we know it is mass of the body. Okay. Then this is what we have studied. Then third point you have learned was in the strength of materials you have studied. Stiffness of a spring you have learned. Then if two springs are connected, depending on their connection, two ways you can connect them. Springs in series, springs in parallel. Let us see what are those characteristics and that we apply here. Then equivalent stiffness of spring system. That third point you will write here. Equivalent stiffness of spring system. Ke. Springs in series. Springs in series. What is the characteristic of springs in series? No question of sharing the load. No sharing of load. W is taken by both springs. Whatever series W, 10 springs are attached one below the other, bottom you apply load W say. W will be taken by all the springs. That means each spring will take load W, no sharing. Is taken by both the springs. Next, this is how it looks like. First spring, second spring. You apply load W, let us say. This is spring K1, spring K2. Okay. Now, when you apply like this, KE, equivalent spring when you want to find KE. You see here, what is the load taken by K2 spring is W. How? Stand here, look down. Load is W. Same load, no question of sharing. This will take W. Stand here, look down. Axial force. Stand here, look down. As you have found in the axial force in a member, one member is L1, L2, L3, AE, 2AE, 3AE, like that is there. When you pull them with the ends, each member will take the same load. W, W, W only will take. So that is called series connection. Springs, shafts in series, springs in series, bars in series, strength of materials you have studied. Similar to that is this one. Then if you want to replace equivalent spring, what is the meaning of equivalent spring? The stiffness of the group of springs must be replaced by a single spring whose stiffness is such that it should give same deflection. In the process, you have learned that Ke is K1 K2 by K1 plus K2. Actually 1 by K is equal to 1 by K1 plus 1 by K2. Then finally it comes like this. That story I think you might have studied. This is no W is taken by both the springs. Then second type of is springs in parallel. What is the characteristic of parallel springs? W is shared by both springs. If two springs are there, they will share. Load will be shared. There, all springs will take W, W, W only. Now, for that how the connection should be made? This is the first spring. Second spring, apply load W. This stiffness is K1, this stiffness is say K2. Now when you pull them, your load W, part of the load is taken by K1, remaining part is taken by K2. If at all they tell you that it is displaced horizontally or in the process of sharing or load where you have to apply so that it will remain horizontal type problems you studied in strength of materials. So to that extent not required. If you apply load W, how they will share? K1, then part of the load is taken by first spring, remaining is taken by second spring. Then if you want to find the equivalent stiffness, you want to replace these two springs by a single spring. That spring stiffness must be like this, K1 plus K2. This is springs in parallel. So whenever you see that whatever load you applied, it is shared by the springs, it is the parallel connection. Not only here, strength of materials, if the shafts are connected in parallel, say, that means when you apply torque on a shaft, two shafts are together connected. Then if the torque is shared by two shafts, means it is a parallel connection. Same torque is there everywhere, let us say, all the shafts, then it is a series connection. So K is K1 plus K2, or in this case both springs are under tension, but they share. Not necessary that they should be under tension and share. It can be one is under tension, one can be under compression, but sharing is there. W is there. This is spring K1, let us say, this is spring K2. It is fixed here. Now when the W comes down, what will happen? Part of this load is taken by the top spring and it is under tension. Remaining part of the load is taken by the bottom spring and it is under compression. But sharing was there. So equivalent stiffness of the spring is again K1 plus K2. This is also springs in parallel. It is one below the other is there, that does not mean that it is series. Is the load shared by the springs or not, or load is there for all members, the same load W is there, depending on that series or parallel connection. So this is what you have studied in the strength of materials in the torsion chapter. Okay, now with this understanding, this much understanding is enough for the dynamics problems that you get in our structural analysis. Only difference is, here springs are given, we will replace them with the stiffness of a beam or stiffness of a frame, that's all. How to find stiffness of a beam? Beam's stiffness means strength of materials you have studied. Frame stiffness means moment distribution method you have studied. Those concepts you plug it and stick it. 30 seconds time you have to complete. Now let us see the numericals. First question, fundamental period of vibration. Period of vibration of the system shown in figure. Neglect self weight of beam. You are given a cantilever beam like this, okay, and connected to that is a spring. To that you have a mass of 50 kgs. This is mass directly he has given. Its stiffness he has given 1000 newtons per meter. This length, let us say AB. Flexural rigidity is also given 5000 kilonewton meter square. Length is 2 meters. Okay. So you have to find the fundamental, that means time period of vibration you have to find. Now it is a free vibration, no damping, because nothing has mentioned about that. So what we do is we replace it with our known thing. This is a cantilever beam spring. You write cantilever beam in terms of a spring stiffness. Cantilever beam subjected to point load. I have given you the stiffness of the beam, flexural stiffness of the beam. So flexural stiffness, spring stiffness. Here this spring is axially loaded, stiffness we know. This beam is flexurally loaded, whose stiffness also we know. So we write in terms of the stiffnesses. So this is what we have studied. Note 1. K is equal to stiffness of cantilever beam loaded at free end. It is like W by delta, because if it all moment is there, we could have written m by theta, ei by l we could have written, but it's like a point load, 50 kg is acting. W by delta means WL cube by 3 ei. This what I have given. So you will get 3 ei by L cube. Next, second point is whether they are connected in series or in parallel. On the first spring you stand here, look down. What is the load? 50 kgs. It is pulled with 50 kg. Stand on the beam, look right side. How much load on the beam? Same 50 kgs. No sharing. So it is series connection. So it is a series connection. W is not shared. So same W is acting. Same W on both springs. So series connection. So that cantilever beam, you replace it with a spring like this. Then already spring was there, you keep that as it is. Mass is 50 kgs. This stiffness we know K1, 3 EI by L cube. 3 into EI he has given 5000 kilonewton meter square. Okay, 3 into 5000 kilonewtons per meter square by L cube. That means 2 cube. That means 15,000 by 8 kilonewtons per meter. This one K2, he has given 1000 newtons per meter, or we can say 1 kilonewton per meter. Okay. Now this is K1, K2. Now its equivalent stiffness we can find. Ke is equal to K1 K2 by K1 plus K2. K1 is 15,000 by 8 into 1 by 15,000 by 8 plus 1. This 15,000 by 8 plus 1, you can take it as 15,000 by 8 itself. Why? As I told you in the temperature stresses chapter, this what we have given earlier. Temperature strain when you are taking, the change in length by original length, delta L by L when we have written, delta by L we have written. This is alpha TL minus delta by length is L plus alpha TL. Like this we have written. When compared with the L, which is in meters, alpha TL is very less. So you round it off to, here only in the denominator you took it as 0. You wrote it as alpha TL minus delta by L. In the temperature stress, in the two hinged arches I have given you this explanation. That small quantity when connected with a very large quantity, only in the denominator you can neglect. Here you cannot neglect because this is small quantity, this is small quantity. Now come to this one. 15,000 by 8 is a very large quantity, 1 is very less. So you can round it off to 0. This we can write it as 15,000 by 8 by 15,000 by 8. You will get 1. 1 kilonewton per meter. Okay, so equivalent stiffness. For this you don't require calculator. This idea you should get. You should not try to again add them and waste your time. Large quantities per small, cut it. If you are forced to calculate it, then immediately stop. That is not the way to do the problem, then how to get out? Think only 10-15 seconds. If you cannot get out, if you are forced to calculate, leave the question, go to the next problems. Because we cannot afford to waste the time. Instead of calculating, supposing that you wasted in the calculations by say 4 minutes time or say 3 minutes time you wasted in getting exact value, we may get full marks, but some other place 2 questions gone, so you cannot win the game. Where you get a very tough question where calculations are more involved, let us say, you resign from that question, attack other problems. In the end, if you find time, you meld with that question, otherwise leave it off. Still you will get very good rank. First rank holders will do that only. Where it is completely time consuming, calculation intensive, come back. Finally, we should get more marks, more score, more correct answers. That's all. Not only one question we have to solve. This I told you, round it off to this 15,000 by 8. So you get 1. Now, this is 1000. This value will get 1 kilonewton per meter or say 1000 Newton per meter, whatever way we can write it. So equivalent stiffness is 1 kilonewton per meter or 1000 newtons per meter. That's all. Now third point is time period is 2 pi root W by kg. That means we can also write this value as 2 pi root m by k. Mass he has directly given 50 kgs by k is 1000. Once mass is in kgs, the stiffness must be in newtons only. So 50 by 1000. So you will get 2 pi by 100 means 2 pi by 10. So square root of 5. Approximately 5 means approximately 2 like that you will get it, or 2.1 that way. 4 pi by 10. So approximately you can calculate it as 1.4 seconds. To evaluate this you don't require calculator. 2 into pi, 5 means approximately 2 you take it. 4 pi, 0.4 into pi, 3.14 into 4. So approximately 1.4. So other 1.4 approximate value selected, enough. Next, this is about the beam. Now, if the frame is given, frame stiffness also we know how to calculate. Next one is determine the time period of horizontal vibration. See, horizontal vibration of the frame shown in figure. Shown in figure, supporting a load W. At center. Neglect mass of frame. Now we have this is a portal frame. This point, let us say A, B, C, D. This EI value, he says infinity. If EI is not infinity, finding the stiffness of the frame becomes difficult. Means it's a time consuming process. Finding stiffness itself takes 2 minutes or 3 minutes time, say. Then no point in answering also. We don't solve. EI is infinity and he has kept a weight W. Length is say H, I. Now, stiffness of the frame for horizontal vibration, first we have to, for horizontal load we have to calculate. In this case, horizontal vibration means you have to push horizontally and leave it and it will vibrate. Time period is asking. So, when you are pushing it horizontally, what is the load required to produce unit displacement? We have to calculate. Supposing that on this frame, if I push a load W, say P, say, this will take some load, remaining load it will take. So it is like a parallel connection, not a series connection. So that first you should understand that point. So that is a first point. Stiffness of frame for horizontal load. K is stiffness of frame for horizontal load. Because he is asking horizontal vibration, then horizontally what is the stiffness you have to calculate. Now you see, if I fix this a hinge support, keep it hinge as it is. EA is infinity, that means I can take it as fixed support. If I push it by delta, what is the force required? This we have learnt. This is the deflection profile A, B will go to B dash, 90 degrees maintained. This is delta, let us say. How much you have studied? The moment developed here, it is 0. Here fixed end moment is 3EI delta by L square, reaction. Then what is the action here, HB? 3EI delta by L cube, this is H, say. So you will get H square, 3I delta by H cube. This what I told you in the moment distribution method, sway is there. For delta deflection, you must, this is the action. If 3I delta by H cube amount of force if you apply, it moves by delta. Now I don't want delta, I want it to be 1. If delta becomes 1, then HB becomes stiffness. Load required to produce unit deflection. If delta is equal to 1, then HB becomes stiffness. Stiffness of column for horizontal load. Okay. So now let us make it delta. So K1 let us call it. 3EI delta by L cube. Now delta becomes 1. So 3EI by H cube. This also H. Since your applied load is shared by 2 columns, it is a series connection. Since applied horizontal load is shared by 2 columns, it is a parallel connection. Equivalent connection is parallel connection. This is the wording important in the exam. Is it whatever push you apply, is it shared or both columns take WW? Accordingly, now your equivalent stiffness is K1 plus K2 because only 2 columns are there. So 3EI by H cube, first column, plus 3EI by H cube, you will get This is the equivalent stiffness. So in the exam, our task is only to find the equivalent stiffness of the column. Now time period. Second point is T. Time period. This is time period is 2 pi square root of W by K into G. 2 pi into square root of W by K. K how much? 6 by H cube into G. So you will get one of the options is like this, 2 pi into W H cube by 6 EIG. Expression may look complex, but this comes from this only. 2 lines. Okay. So time period is so much. Next one. Now we'll see the next question. A single degree of freedom system of mass freedom system of mass 22 kgs and stiffness 17 kilonewtons per meter vibrates freely. Vibrates freely. If damping in the system is damping in the system is 2%, the cyclic frequency and damped circular frequency. Damped circular frequency respectively are nearly, means approximately you have to make it, or nearly 4.4 hertz and 0.88 radians per second. 0.88 hertz and 27.8 radians per second, 4.4 hertz and 27.8 radians per second, 0.88 hertz and 0.88 radians per second. The question is cyclic frequency, damped circular frequency, F and omega they are asking. Allotted time is 30 seconds and we don't have to use calculator. And damping in the system, he says around 2%. 2% means almost negligible. It's like a free vibration without damping case. So small it is. Then your same formulas we can use it. The natural circular frequency, cyclic frequency, they differ by 2 pi. F is what? Circular frequency means you have given you 2 pi by omega. So 2 pi by omega is the time period. Circular frequency is omega by 2 pi. Okay, this is the one we have learnt, right? So that natural circular frequency, if you divide it by 2 pi, you will get the cyclic frequency. So second quantity, circular frequency means this one. Second quantity should be divided by 2 pi so that I should get first quantity, right? If I divide it 0.88 by 2 pi, will it get 4.4? I will not get it, cancel it. If 27.8 by 2 pi, that means 2 pi means approximately 6 you say. 27.8 by 6 means around 4 you will get. 4 is not there, cut it. 27.8 by 6 approximately 4, so tick it off. 0.8 by 6 cannot be 0.88. This is how the process of elimination. Otherwise, you cannot get the exact expressions and calculate it because you don't have calculator in the first place. So, the question of calculations, exact value for the cyclic frequency when damping is there, you cannot manage. Okay. So, just what is the difference between the cyclic frequency, natural circular frequency, how they differ from our engineering mechanics, mechanical vibrations point of view. That you see, from that you can get it. Okay. So this is how the C is the answer now. Next one, you see here, an RCC slab, here itself I will write. An RCC slab, this is M25 grade. Of dimensions 5 meters by 5 meters by 0.15 meters. Means slab 5 by 5 by 1.5 means that slab is of infinite stiffness. Flexural stiffness is approximately equal to infinity. Is supported on 4 square columns. Earlier I gave you problem with 2 columns, now 4 columns. Is supported on 4 square columns. M25 4 columns of M25 grade and of side 400 mm. The clear height of each column, the clear height of each column is 3 meters. Assuming rigid connections, you see it is a rigid connections. Even if they don't give also, we assume rigid connection only, so that the joints will not rotate. Time period of vibration, time period of vibration of slab along horizontal direction. Along horizontal direction is nearly. That's how the question is given. Now you see front view I am showing. This is a slab. It is 5 by 5 meters. 5 meters. Thickness is 0.15 meter. The perpendicular direction also 5 meters. There is a column here. Fixed at rigid connections. Column height, say it is 3 meters here. We could show only 2 columns, but other 2 columns are in the perpendicular direction. So totally 4 columns are there. Of size 400 by 400 means 0.4 meters by 0.4 meters. Here also column is square, 0.4, 0.4. Height is 3 meters. Okay, like this they have given. Then you see now if you have both ends fixed one. First point. If I push the slab, that push will be shared by now 4 columns. So it is a parallel connection. So first point is K. K means stiffness of frame in horizontal direction. Since horizontal load is shared by 4 columns, it is a parallel connection. First that idea we should get. So it is both ends fixed one now. First column, let us say AB, you take it. All are rigid connections, A, B. Push it to the right side. The deflected shape is now like this. This becomes now delta. Now this is the moment 6 EI delta by L square. 6 EI delta by L square, and force required is HB is equal to 12 EI delta by L cube. This is what I have given you in the moment distribution. If delta is equal to 1, HB becomes stiffness. Stiffness of column for horizontal load. Okay. If you push at horizontal load must be at top. For that case only, this becomes the stiffness of the column. Okay. So now 4 such columns are there. Okay. Now we will get KE is equal to equivalent stiffness of 4 columns. So 4 into 12 EI by L cube. We will get 48 EI by L cube. Okay. Now in this, what is Young's modulus? E stands for Young's modulus of concrete. We know it is from concrete we have learned 5000 root FCK. FCK has given 25 grade. So you will get 25,000 newtons per mm square. Now we will write everything in terms of Newton meter square. So 25,000 newtons per mm square means mm means 1 by 1000th of mm. So when it goes to the top, it will become 25,000 into 10 to the power of 6 newtons per meter square. Then I value. Actually it is BD cube by 12. We have a square column. Each dimension is 400 mm means 0.4 meters. 0.4 into 0.4 cube by 12. Keep them as it is because calculators are not permitted. In the end we will cancel them. Simple calculation only you will get. So L value we know 3 meters. Now equivalent stiffness KE becomes 48 EI by L cube. 48 E means 25,000 into 10 to the power of 6. I means 0.4 into 0.4 to the power of 4 by 12. EI value into L cube means 3 cube, meter cube. Okay. Now time period. He is asking you to find time period. T is equal to 2 pi square root of W by K into G, square root of weight of the slab. Weight of the slab means, because only weight of slab was there, volume is 5 meters by 5 meters by 0.15 meters into 25,000 newtons per meter cube. This is what we know. So W will write here 5 into 5 into 0.15 into 25,000 by K. Equivalent stiffness is how much? 48 into E is 25,000 into 10 to the power of 6 into 0.4 to the power of 4 by 12 means here into 12 into 3 power 3. G means into 10. This is the calculation. Now how we should simplify? 2 pi, this is 2 pi also is there here. So 2 pi as it is, you will keep it. See, if 2 5s are there, this cut, you write 1 5. Next, 25,000 cut as it is, you keep it off. 0.15 is as it is now, keep it as it is. This 12, I can write it as 4 into 3. So 3 into 3 to the power of 4, now I can write 3 square. So 3 to the power of 4 gone. 4 I can write square root of 4 means into 2. So this we have written, this we have written. Only 0.15 is left in the numerator. So square root of 0.15. Denominators let us see. Here 48 is there. 16 into 3 I can write. This is 16 into 3. So 16 means when you take it out 4 you will get it. 4. Root 3 as it is will keep it. 10 to the power of 6 when you take it out 1000. So this is gone now. 0.4 to the power of 4 square root means 0.4 square. Now what is left out? 16 we have taken it out. 3 into 10, 30. So into square root of 30 we have. Right? Everything is removed. So now this will become like this. This is how you can calculate. So 2 pi into 5 into 3 square into 2 by 4,000. So 4 you can take it as is 4 into 1000 into 0.4 square into square root of 15 by 30. 15 by 30 means how much? We can write it as, this we will write it as square root of 15.15 it is. 0.15 you write it as 15. Okay, 2 zeros. Here 3 zeros extra you will write. So that means 3000 means 2 zeros you can take it out. It is like 15 by 30 into 10. So this will write it as 2 pi into 5 into 3 square into 2 as it is will write it divided by 4 into 1000 into 0.4 square. This 3000 we are taking 10 out. So 100 is gone. Root of 15 by 30. 15 by 30 means 1 by root 2. 1 by 2 actually 1 by root 2 you can take it. Now what can be cancelled? 2 cancels out, 4 you can cancel, right? So the remaining values are like this. So time period you will get, this is what you have to calculate, pi into 5 into 9 into 9 divided by 0.16 means 0.16 into 10,000. Okay, into 1 by root 2 means we know 0.707. This, now we can simplify this one. You will get around 0.06 seconds. Time period is 0.06 seconds. Finally, this boils down to this much simple calculation. So now we will see this is about the free vibrations, without damping, free vibrations. Okay. Okay. Now we'll see the workbook solutions. First one is the determinacy and indeterminacy. Okay. Now, first chapter, determinacy and indeterminacy. First question is, a guided support as shown in figure below is represented by 3 springs, horizontal, vertical and rotational springs. So there was a roller support, we can take it, this is a beam. Okay. So it is like a guided roller support. Figure below is represented by 3 springs with horizontal, vertical and rotational stiffnesses kx, ky and k theta. X direction, y direction, k theta means rotational stiffness. The limiting values of kx, ky, k theta are x direction, this is x direction, y direction. Okay. Now this is the problem, guided roller support. The stiffness means force required to produce unit displacement. If you have a guided roller support like this, it can only move up and down. Even if you apply infinite amount of force also, it will not move, leaving the support, it will not come out, right? That means x direction, its stiffness is infinity. That means infinite force you apply also, that unit displacement will not happen. So x direction kx is infinity. Y direction is a roller parallel to the plane of roller. If you tap like that also, it simply moves because it cannot offer any reaction. So zero force is required to produce unit displacement. Limiting value, we can say its stiffness is 0 because freely it will move up and down. As we told you, in the guided roller support, if you have that guided roller support, if you have tried to rotate, it will not rotate because there is I told you there is a channel like this, it will hold. It will permit only upward, downward movement only. If you want to rotate, it cannot be rotated. So infinite moment you apply also, it cannot rotate because it is rigidly connected. So k theta is also infinity. So x direction infinity, y direction 0, theta is infinity. So correct option is all infinity, 0, infinity means A. First question is option A. Next, second one. This is the first question. First chapter, first question. Now second question. Beam AB supported, the directions of the reactions are also given by. See, the free body diagram he is asking. We have a simply supported beam subjected to some load 2 ton, angle of inclination 60 degrees, and you have a roller plane. This is the roller. Okay, these directions are A, B, and C. This distance is 3 meters, 1 meter. Okay. Now, what is the free body diagram? Free body diagram of the beam. Free body diagram means it is the diagram of a body on which what others are doing you have to show. Now, if you show the 3 reactions on the member AB, how many forces are acting? Only 3 forces are acting. What are they? Hinge support will exert how many reactions? 2 reactions, VA and HA, and the resultant reaction is like this, RB. Only one reaction. I can replace this VA and HA by its resultant reaction RA. Now, in the cables chapter, I told you 2 concepts. How to keep 2 forces in equilibrium. To keep 2 forces in equilibrium, they must be equal, oppositely directed and collinear in action. If 3 forces are there, to keep the 3 forces in equilibrium, they must be concurrent and coplanar. Otherwise, you cannot keep 3 forces in equilibrium. If you replace VA and HA by RA, now there is only one force here, RA. This is RA, 2 ton, RB. Only 3 forces are there. For them to be in equilibrium, they must be concurrent. Now let us see where they are meeting, which diagram they are meeting, you see. See, this react, when I am pushing it like this, they must go this way only. So, the 2 reactions, see, the resultant reaction will go upward, this is upward, and they will meet at one point. If you extend this line, supposing that the resultant RA is something like this, say. Okay, so extend this line somewhere here. If you extend this line, supposing that RB I am extending here, say, then the RB reaction or RA reaction should be such that it should move like this. The resultant of V and HA direction cannot be this way. If it is that way, means that 3 forces are not meeting at one point and it won't be in equilibrium. So it has no choice. Third reaction, RA, has no choice. It has to be like this only. So now these 3 forces are meeting somewhere in air. Anywhere, but they must be concurrent. Now they are coplanar. This is upward, and this is acting like this. Because RB now, when force is applied this way, it has to act perpendicular to that only. It cannot go down way. So the 3 forces will meet somewhere here. So your correct option is, first option they have shown RA downward, which is not possible. Now RA is upward, second option is given correct. But RB they have shown vertical, so B is wrong. C, you see, RA, RB and 2 tons. It is in our free body diagram. So correct option is C. This is the point. To keep 3 forces in equilibrium, they must be concurrent. At ABC is over. This point, let us say D. They must be concurrent at D. Okay. Now, then, why the D option is wrong is they have shown the reaction RB down. So it cannot be downward, because when I am pushing it this way, the reaction will act like this. When I am pushing it down, the reaction must be upward. Okay, like that. So that's why D option is wrong. I think you followed. This is the idea we should get in the exam. This means how you have to read the notes. I am telling how carefully you must read the notes. Any question given will be somewhere in our notes only. Next, third one. What is the DS? Degree of static indeterminacy. Plane truss shown in figure. See, something like that, a truss is given and it is added this way. Wherever circles are there, that means they are joints only. Okay. Now one more triangle was formed here. It is like a complex truss, we can take it. Okay. Now this is one more line, it went this way. Another line went this way. These two are hinge supports. Okay. Into formed, triangle formed. Okay. This is the question. How many reactions are possible here? This point, if you take say AB, VA, HA, VB, HB, right? So number of reactions are 4. Equations of equilibrium available, we will write it that way. Total we'll see. Number of joints, 1, 2, 3, 4, 5 joints. Number of joints are 5. Number of members, first periphery you check it. 1, 2, 3, 4, 5. Periphery is over. 5, 6, 7, 8, 9, 10. Number of members are 10. That's how you will count them. Otherwise you can say 4. Here 3 is 7. 4 plus 3 is 7. 8, 9, 10. That way also we can take it. You can count it. Static indeterminacy means total number of unknowns. M plus R minus 2J. Members are 10. Reactions are 4. Minus 2 into 5. 14 minus 10, 4 degrees. So static indeterminacy is 4. So third question, B is the option. DS is 4. Next, fourth question we'll see. List 1 and 2 is asking you to find the static indeterminacy. We have a fixed arch is given. This is the fourth question. For this one, static indeterminacy how much? DS is R minus S, 6 minus 3, so 3 degrees. So this is ASA. For this one, DS is 3. Next, second option is like this. This is A. B. We have a continuous beam. Hinge was there. Like this. Okay. Now, for this one, what we have to answer? Now, if you take loading is not given, general case you take it say 1, 2, 3, 4, 5, 6. 6 reactions are there. So, internally one equation of equilibrium, Unknown reactions are 6. Equations of equilibrium are 4. Sigma x, sigma y 0, sigma m 0. Bending moment at A. This point we take say A. Bending moment at A is equal to 0. So static indeterminacy will become R minus S, 6 minus 4 is equal to 2. So B, you are getting static indeterminacy, let us say 2. Then third one he has given generally in any continuous beam, whether even if they give you like this, the horizontal reactions we assume that not develop. It is only simple support, that's all. We don't pin them. So it is simply resting on these supports. We should not assume that there is a hinge kept there. Generally that hinges are kept to prevent the translation. One place if you hold it, all other places automatically they don't move at all. So one more hinge pin is not required. Simply resting will be there. So horizontal reactions should not be shown. Now if you take this point, there is a hinge here, hinge here. Okay. This is the problem. How many cuts are required? 1, 2. Number of cuts are 2. Here minus 1, minus 1. So for this one static indeterminacy is 3 into number of cuts are 2 minus A, B, let us say minus 1 at A, minus 1 at B. So 6 minus 2, 4. So for this one ds is 4 degrees. Now you see 3, 2, 4. Which one is matching? A is 3, A1, correct? B is, we are getting B2. We will calculate all otherwise. C, D. Member was like this. A gable frame given first. Okay, hinge was there here. One more gable. This is the problem. Now you take here number of cuts are again 1, 2. Here minus 1, minus 1. So static indeterminacy is 3 into number of cuts are 2 minus 1, minus 1. Minus 1 at A, minus 1 at B. The cantilever method when you take 6 minus 2, 4. Now correct option is first one A1, 3 matches. Then B is 2, 2 is there, 2 is not there. 5, 4 is given. Now in this case, if you take 3, 4, 5, 6, unknown reactions are 6. Equations of equilibrium 4. 2 itself is missing. Okay, now 5 first of all is not there. 4 is there. D is there. So you have to select like this. A1 correct. C 4 degrees. So C 4. D 4. Next B 3 you are getting. 5. Now this A3 is correct. A1 is correct. This is how you will get it. A1 correctly matched. Next B let us wait. Then C you are getting 4. C4 means C4. Then D also 4. So 1, 4, 4. So only option left out is D. So we answer fourth option as D. Now let us see what he wanted. See, as per this one you should get 3 means 5. Instead of 5 we are getting 2. Don't worry about that. Because the way we have drawn, there might be something, one more span or there must be a typographical error. In this case, here one fixed support, hinge, hinge, hinge. So you are getting only this much. 3, 4, 5, 6 and equations of equilibrium are 4. So 2 is the correct option. Since it is not matching, what we will do is, for correct one is this one. 1, A3, B2, C4, D4. So sometimes if any one mistake was there, any other 3 options are matching, then best option is this one only. Maybe some printing problem here. Okay, like that. Next, fifth point, pin jointed frame shown in figure. Next, fifth question. Now, pin jointed frame shown in figure, you have to calculate. Now, you see, in that number of reactions, suppose they have shown one triangle, this a roller, this you extend it, straight line it is. Okay, now say horizontal one. Some loading was there here. 1, 2, 3. There is only a vertical loading. Anyhow, horizontal reaction is 0. It doesn't matter for us. Now, so many members are there. Number of members peripheral, if you take it 1, 2, 3, 4, 5, 6, 7, 8, 9. So number of members are 9. Even otherwise also you can make a triangle, 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 triangle formed. This is in 2 plus 1, 3 reactions. It is just a stable frame. So it is a perfect frame. Members are 9. Then unknown reactions. Number of reactions are 3. Number of joints are 1, 2, 3, 4, 5, 6. So static indeterminacy is m plus r minus 2j. So 9 plus 3, 12 minus 2 into 6. 0 implies determinate. And m is equal to 2j minus 3 followed. Number of members are 9. 2j means 2 into 12 minus 3. If number of members are exactly equal to 2j minus 3, it is a perfect frame. So perfect truss. Frame he has given, but okay, no problem. This is A. It is a perfect truss. Number of members is equal to 2j minus 3 tallied, because a triangulation formed in a simple truss, that is the condition. So it's like that. Next, static indeterminacy for the given 2D frame. Now we have to find ds. fixed here. There is a hinge. Two members are like this, 1, 2. And in the second member onwards, it went a thing like this. Again, it is this way. Fixed here. Here also hinge, internal hinges. 3 internal hinges are there. Here also one hinge, like this. Now you see, what is the static indeterminacy? For this, how many cuts are required? 1, 2, 3 cuts separated. Here, only one cut. Now this is separate. 4. Here, one more cut. So 3, 4, 5 cuts are required. Number of cuts are 5. And to make stable cantilevers, you have to add how many hinges? Here there is a hinge. It's not a stable one. Cantilever you are not getting. So you have to fix it. Unnecessarily fixing, so -1. Here this will rotate, so you have to fix this one with one moment reaction. B also you have to make one fixed one. Here only one moment you have to add. So -1. Now static indeterminacy is 3 into number of cuts are 5 -1 at A. These are to make stable cantilevers. So -1 at B, -1 at C, D. So 15 minus 4, 11. So static indeterminacy is 11 degrees. So sixth question, D is the option. 11 degrees. Next, seventh question. Static indeterminacy of a rigid jointed frame. This I have solved in the class. A rigid jointed frame. This is a rigid jointed frame connected to a cable. To a cable PQRS. PQRS. Okay, angle of inclination he has given 45 degrees. So how many unknown reactions are there here? Horizontal reaction HP, VP. Then here there is only resultant reaction RS with an inclination of 45 degrees. HS, VS, you can find if RS is known. Theta is known to us. Number of unknowns are only 1 here. So total number of unknown reactions are 3. VP, HP, RS. Only one reaction. Unknowns is only 1. Theta is known. So a number of unknowns are here 1, here 2. So 3. Equations of equilibrium are 3. So static indeterminacy is R minus S, 3 minus 3, 0. So he is asking simply static indeterminacy. Seventh question is A is the option. In the cable problems, I told you how we have to calculate. Whenever there is a cable, their number of unknowns only 1. Because the RS, reaction at S, has no choice other than acting in the direction of the cable. Cable inclination is known, that means R direction is known, that means only one unknown. If I know RS, HS means what? RS cos 45. See here, HS is equal to RS cos 45. VS means RS sin 45. So only one unknown. If I know RS, I can find HS and VS. So it is a statically determinate frame. Next, eighth one. Now static indeterminacy again. Now there is a guided roller support. This is a beam and here there is a roller and here there is a link and it is connected to a member, fixed support. Let us say this is A, B, C, D and E. So you can, this is like a link. You can take our cantilever method also. 1, 2, 3 supports are there. That means you require 3 cantilevers. So make a cut here, 1, this is a cantilever. Make a cut here, this is separate. Now that's all. Only 2 cuts are enough. Number of cuts are 2. Now you must get a stable cantilever. Here already 2 reactions are there. Horizontal reaction it can give, moment it can give. What it cannot give is vertical reaction. So -1. Here roller is there. Roller cannot give horizontal and vertical reactions. So you have to fix it. So I have to add 2 reactions. So -2. Hinge is there. Moment. One moment you have to add it to fix that so that it will not rotate. So -1. Here -1. So you will get static indeterminacy is 3 into number of cuts are 2, -1 at A, -2 at B, -1 at C, -1 at D. So 2, 3, 4, 5, 6 minus 5, 1 degree. So static indeterminacy becomes 1 degree. So DS is 1. So 8th question is B is their answer. Okay. Next. 9th one. Now total degree of indeterminacy of the plane frame shown in figure. All are fixed here. There is one internal hinge. This is a frame. How many supports are there? 4 supports are there. So 4 cuts. 4 cantilevers we want. So 1 completely cut, 2, 3, 4, 5 cuts. Number of cuts are 5. Now there is a hinge at A, let us say. To fix it you require only 3 movements because 4th movement is not unknown. So unnecessarily you are fixing 3, you are adding 3 movement reactions to make it as a rigid jointed one. 4th movement is now summation of 3 is the 4th one only. So only 3. Unnecessarily you added 3 movement reactions, so subtract -3. So static indeterminacy is 3 into number of cuts, 15 minus 3, 12. So DS is 12. So correct option is C, 12 degrees. Next, 10th question. A plane frame is statically determinate if, now you have a plane frame. In a truss we have taken, for a truss, total static indeterminacy you have written M plus R, each member one unknown, then number of reactions. At each joint we have 2 equations of equilibrium. Why 2J? 2j because at each joint we have sigma x0, sigma y0. Why m unknowns? M because each member one unknown force, one unknown axial force. This is what we have learnt. Now, this is for a truss, for a frame. For a frame, each member, how many unknowns will be there? There will be one axial force, shear force and moments. Number of unknowns, static indeterminacy, instead of m, 3m. Because each member there is one axial force, shear force and moment. 3m plus number of reactions is same. Whatever number of reactions are there. Now j, 3j you have to write because at each joint we have three equations of equilibrium. Sigma x0, sigma y0, sigma m0 also we can write. 3j. So 3m plus r is the total number of unknowns. 3j are total number of equations of equilibrium. 3j because at each joint sigma x0, sigma y0, sigma m0. 3m because for each member 3 unknowns. What is that? Axial force, shear force and bending moment. But whereas the truss only one axial force. At each joint sigma x0, sigma y0. From this you can get this one, 3m plus r minus 3j. So for a plane frame, 3m plus r minus 3j. This is the total static indeterminacy. Now he says a plane frame is statically determinate. ds must be 0. So 3m plus r must be equal to 3c. Number of equations of equilibrium. 3j is here. Number of members, number of joints, number of reactions. 3m plus r is equal to 3j. Number of equations of equilibrium. Equations of additional conditions. 3j. Now this must be 0 if at all. 3j is the each joint we are getting. Three equations of equilibrium. Similar to this one, additional equations come, let us say. Then they also will come here, 3j plus c. So now this we can modify. ds is equal to 3m plus r minus 3j. If at all any internal joint additional equations of equilibrium, like internal hinges are there, say, that point let us say c. Okay. Now if static indeterminacy is 0, then what will happen? It will be determinate. So 3m plus r must be equal to 3j plus c. So number of unknowns, number of equations of equilibrium. C means internal hinges, number of equations of conditions. Equations of conditions means external conditions. Now you see 3m plus r must be equal to 3j plus c. Then it will become statically determinate. ds is 0 means statically determinate. So if at all additional conditions are not there, we can write it 3m plus r minus 3j. r is equal to 3j should be there. If no internal hinges are there, additional equations of equilibrium are there, this will write. If at all c is the additional internal hinges are there, if that comes, then 3j plus extra, like bending moment at c 0, bending moment at d is equal to 0 are there. So like that. Okay. So 3m plus r is equal to 3j plus c. So 10th question is A. This is how we have to deduct. Means reduction of the formulas means from this we know how it came, then how it can come. If at all it is spatial frame, say, For each frame you have 6m. See here, this is plane frame. This is for a plane frame. Then for a space frame, if they give, supposing that, for a space frame, static indeterminacy is for each member 6 unknowns. What is that? 3 reactions, 3 movements. So each member has 3 number of unknowns. So 6m plus r minus 6j. 6j because at each joint we have sigma x0, sigma y0, sigma z0 and sigma mx0, sigma my0, sigma mz0. So 6 equations of equilibrium you will get. 6m because 6 unknowns for each member. What is that? For each member x, y, z 3 reactions, mx, my and along z direction. Mz becomes like a twisting moment. So 6 unknowns for each member, 6 equations of equilibrium at each joint. If at all any additional conditions are there, plus c you have to write. Otherwise 6m plus r minus 6j enough. Unknowns minus equations of equilibrium. So for this frame this is sufficient. 10th question is A is the option. Related details are truss, frame, plane frame, space frame. Next, 11th question. With cantilever ends are given. 4 unknown reactions are there. Number of unknown reactions are 4. Now equations of equilibrium available are only 2. Sigma y0, sigma m0. What are the 4 reactions? R1, R2, R3, R4. So static indeterminacy is R minus S 2 degrees. So statical indeterminate to second degree. 11th question is C is the option. So 4 reactions, 2 equations of equilibrium. Next, 12th one. Plane frame, space truss, space frame. So plane frame, static indeterminacy is 3m, total number of unknowns, 3m plus r minus 3j. Plane frame, 3m plus r minus 3j. So A4, we can take it as A4. Then space truss, static indeterminacy. Plane truss we have written. What is the plane truss? ds m plus r minus 2j. This what you have written. Truss members, again number of unknowns are m only. So number of members are, if in a space truss 20 members are there, 20 unknowns only. Each member one unknown. Number of unknown reactions are. But at each joint, because it is a space frame, sigma x0, sigma y0, sigma z0 also we can write. So m plus r minus 3j. This is for space truss. So for space stress 3J, because at each joint we have sigma x0, sigma y0, sigma z0. So this 3 corresponds to that. 3 equations of equilibrium. So m plus r minus 3j. So 1. B1. A4 B1. Next, space frame. Space frame ds, I have told you 3m. Each member space frame is 6m plus r minus 6j. 6m plus r minus 6j, 2. C is 2. So A4 412. 412 means D. So 12th question, D is the option. Like that. Supposing that if once we know how to get for a plane truss m plus r minus 2j, what is m, what is r, what is 2j, we know. From that all other things, plane frame, space truss, everything we can get. Next, I remove this one. This one I have explained. That same thing they have given in another question. Next, 13th question. The total degrees of internal indeterminacy. Now see, there are 3 hinge supports are there. So 3 hinge supports. So 6 reactions. So number of reactions are 6. Then number of hinges. Joints are how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Number of joints are 12. You can count that. Number of members. See 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Number of members you have to count. They are 18. I am getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Number of members are 18. So total static indeterminacy means m plus r minus 2j. Number of members are 18. Reactions are 6. Minus 2 into number of joints are 12. 24 minus 24, 0. So determinant. Pin jointed structure shown in figure. 18 plus 6, 24. Number of members I think we have to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Number of joints 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It is supposed to be statically determinate, but no option is matching. So actually it should be 0 only. Number of members we are getting 18. 18 members are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So static indeterminacy we are getting 0. We'll keep it as this much only. No option matches. So 13 is 0. Next 14. What is the total? For vertical loading also it is the same way. Whether member forces are 0 or not. General loading only we have taken. Okay. Now what is the total degree of indeterminacy in the continuous prismatic beam? There is a beam like this. Both ends are fixed. Hinge. There is a roller. Vertical loading only. For vertical loading only you have to take, because loading he has given. So that means horizontal reactions everywhere are 0. This point you take, say A, B. You will take the reactions are 0. This HC is also 0. So number of unknown reactions are, for the given loading only we have to calculate. Here how many are there? VA, MA. Here VC. Here some VD. Then VB, MB. So number of unknown reactions are 2, 3, 4, 5, 6. Equations of equilibrium are only 2. Sigma Y0, sigma M0. So static indeterminacy becomes R minus S, 6 minus 2, you will get 4 degrees. So this 4 is given. So 14 is D is the option. Next 15th question. The degree of static indeterminacy of the rigid frame having two internal hinges. You see here it is a rigid jointed frame. I told you rigid jointed frame can be kept on hinges also. So rigid jointed frame kept on a hinge, rigid jointed frame kept on roller. This is a rigid joint. Here also rigid joint. Internal hinges are there. This point you take, say A, B, C, D, E. So again here number of cuts required. Stable cantilever frame. Number of cuts required are 1, 2. Now this is separate, 3, 4. Now this is one cantilever frame. So number of cuts are 4. Now to make it as a fixed one, I have to add one moment reaction, so minus 1. Here roller is there, to make it as a fixed one, minus 2. Here to make it as a this one, minus 2. Roller support. Now here minus 1, minus 1. So static indeterminacy is number of cuts are 4, 12 minus 1, 1 at A, 2 at B, 2 at C. This is rigid jointed. These three members are rigid jointed, kept on a roller. So I have to fix it. So to fix it, I have to add one moment reaction, one horizontal reaction. This diagrammatically also I have shown you in the fundamentals how the rigid jointed one can be kept on a roller. Rigid jointed one can be kept on a hinge support. So that you recollect. So ABC minus 1 at D, minus 1 at E. So 12 minus 2, 2 plus 1, 3, 5, 6, 7. 12 minus 7, 5 degrees. So DS is 5. So 15th one is D is the option. Now we'll see the question number 16. The total degree of static indeterminacy for the truss. It is something like this. Now in this problem, external indeterminacy is not there, one end hinge, one end roller. When circle is there, here also there is a pin. Okay. So total static indeterminacy ds means m plus r minus 2j. Total number of members are, see, first peripheral will count them, 1, 2, 3, 4, 5, 6, 7, 8. Then internal members 9, 10, 11, 12. Then diagonals 13, 14, 15, 16, 17, 18, 19, 20. So number of members are 20. Unknown reactions are 3 only. Number of joints 1, 3, 6, 9. 9 joints are there. So total static indeterminacy is 20 plus 3 minus 2 into 9. 23 minus 18, 5 degrees. So static indeterminacy is 5 degrees. So 16th B is the option. Now we'll see the 17th. Now we'll see the 17th question. We want to find the decay of the inextensible beam. Decay when inextensible. This is the case. Internal hinges are there and there is a roller support here and also here. Okay. Now first you take the case of A, B, C, D, E, F. Decay when extensible you take it, then you can take inextensible means number of members you can subtract. Decay when extensible. Here how many decay? Only one rotation. Here decay is 2. This is at C you have a internal hinge which is called moment release. I told you about the axial thrust release, shear release, moment release. Wherever you have them, decay is 4. So here decay is 4. Here also decay is 4. Here decay is 2. Here also decay is 2. So when extensible, this is the case. 1, 2 plus 1, 3, 4 plus 3, 7, 4, 11, 4, 15. So 15 degrees. But inextensible, decay when inextensible. Decay when extensible minus number of axially rigid members or number of independent displacements prevented. How many are prevented? There are how many members? 1, 2, 3, 4, 5 members. So 5 members, 5 in its longitudinal direction, the displacements are not possible. So you remove 5. So 15 minus 5. You will get decay 10 degrees. So 17th question is D is the answer. Similarly 18th question we will write here. Stat ds and dk we want to find. Now this is the problem. There is a hinge support here. There is a member. There is a roller support here. and here also a guided roller support, and here there is a, like this is there. Okay. Now ds and dk, static indeterminacy, when you want to find number of cuts, we will see how many cuts are required. There are 4 cantilevers, 4 supports, so 4 cantilevers you should get. This point you take say A, B, C, this last point you take say D. How many cuts are required? 1. Now if I have to cut them, 3 here. Now this is a cantilever. Here 1 cut is sufficient. This is a cantilever, this is separate. So 3, 4, 5 cuts. So number of cuts are 5. Now here it should be stable cantilever, means fixed support should be there, but hinge is there. So you have to fix it. So we have to add 1 reaction extra. Unnecessarily we are adding. So 1 you subtract. Here 2 you subtract. Here 1. 1 horizontal reaction you have to add. Unnecessarily added, you subtract. Here hinge is there. If you apply, it must be stable. If you apply plus 10, here minus 10 will be there. So only 1 you have to add. Other one is known to us. So static indeterminacy you will get 3 into 5 cuts, 15 minus 1 at A minus 2 at B minus 1 at C minus 1 at D. See 2, 3, 4, 5. 15 minus 5, 10 degrees. So static indeterminacy is 10 degrees. Now you see 10 already tallied, but 2 options have same 10. Then 30 or 26 2 are there. Now we have to see that point. Now dk we will see. Otherwise, if only one option 10 is there, then that we could have answered without finding dk. But 2 options have same 10. So you have no choice. Here dk is 0. Here dk is 1. Here kinematic indeterminacy is 2. Here dk is 1. Here dk is 3. Here also dk is 3. dk is 3. Here also dk 3. If this floor level, again dk is 3. dk is 3. Here dk is 4. dx, dy, and 2 independent rotations. Okay. So dk is 4. If you add them, dk when you are finding 0, 1, 2 plus 1, 3, 3 plus 1, 4, 4 plus 3, 7, 10, 13, 16, 19, 19 plus 3, 22 plus 4, 26. So 10 and 26. So 10 and 26 means 18th D is the answer. Okay. Now 19th question. Here itself we can write. Now kinematic indeterminacy we want to find dk. The beam is like this. Fixed is a hinge support, internal hinge, roller and roller. Okay. Now this is the problem. Now dk, when extensible case if I take it, he didn't mention anything. So here dk is 1 hinge support. So here dk is 4. This is moment release. Here dk is 2. Here dk is 2. X displacement and rotation. Here dk is 0. Now you see 4 plus 1, 5. 5 plus 2, 7 plus 2, 9. So dk you will get 9 degrees. So 19th question 9 is there. So B is the option. Next, 20th. 20th question dk. How much? Kinematic indeterminacy of the plain truss. Now the structure is something like this. Okay. Now it goes say something like this. This and this is connected. This is connected. And this one, let us say this way. And this comes like this. Like this was there. Here there is a roller. Okay, this is the point. Now dk when you want to find, here dk kinematic indeterminate rotations we should not count. Okay, dk is 0. For trusses dk, for rotations, for trusses rotations we should not count it. So dk here it is 2, dk is 2, 2 here, 2 here, 2 here, 1 here. Now you see how many you will get. 2 plus 2, 4, 6, 7 plus 4, 11. So dk you will get 11 degrees. So 20th question, A is the option. Now if you see the 21st question, which one of the following structure is statically determinate and stable? Statically determinate and stable. Now you see, if I take this structure, a rigid jointed one. This is a roller support here. Now how many reactions are there? 1, 2, 3. B, you take HB. Okay, 3 reactions. Okay, so ds is equal to r minus s. 3 minus 3 is equal to 0. Determinate and stable. Now you see 3 reactions are non-parallel and non-concurrent. So 0 means determinate. So this is stable and determinate. Okay, next B. This is the A diagram he has given. So B is fixed beam he has given, but central one floating hinge. If you take the general loading, say unknown reactions are 6. A, B, let us say. 3 reactions HA, VA, MA, HB, VB, MB. Equations of equilibrium are 4. sigma x 0, sigma y 0, sigma m 0, and one internal equilibrium equation. These are called additional conditions we have, that is at C it is 0. So static indeterminacy is r minus s, 6 minus 4 is 2. 2 means indeterminate. This is stable and indeterminate. He is asking which of the following are stable and determinate. Next, third point, third option, if you take it, he has given like this. There is a, at this instant, at some of the loading position, he says that there is a reaction here. This point, let us say A or A. The meaning of showing like this is that the reactions are acting like this, RB. So the resultant reaction at A is in the line of action of the RB. So these two reactions, only two reactions were there. So moment reaction, now since they are coinciding, non-parallel, non-concurrent should be there. They are parallel now. Only two reactions are developed and they are parallel. So it is unstable. Two reactions are parallel. So if at all you apply any moment, it will simply rotate because these two forces will not form a couple. But after rotating by some distance, maybe say 5 degrees it rotates, then roller will go up, so that means reaction will be somewhere here, then couple will form. RB, RA couple will form and moment it can offer resistance. But in this condition, it cannot offer any moment reaction. So since these two reactions are parallel, the third reaction, we can say that third reaction put together is missing, or we can say that couple cannot form. That's why it is unstable. Next, fourth one, D he has given like this. This is comes under geometrically unstable. More specifically, geometrically unstable at this constraint. In this case, three reactions are here. Actually, three reactions are there, but the resultant of the two reactions are they are parallel now. So the geometric condition is not proper. They are parallel. Here also geometrically unstable. Three reactions are there, but still unstable. The reason I told you why it is unstable, if minimum three reactions are developed but still it is unstable, we call it as geometrically unstable. Just tap it, it will move. Here, just tap it, it will rotate. It will not translate, but it will rotate. Because the three reactions resultants are concurrent, they are meeting at one point. Parallel and concurrent. In this case, you can write concurrent also. Meet at the same point. So geometrically unstable. So he says, out of these four, which of them are stable and determinate, means only A. So 21st is A is the option. Then 22. The plane structure shown in figure is, this I solved in the class. Same problem they have given. It is stable and determinate. 22nd question C. This we have solved in the class. Same problem we have solved. It became stable and determinate. 23. Prismatic beam. Consider the following statements. They have given you a prismatic beam. There is a central hinge like this. I told you that if at all there are three hinges with central floating hinge, it is always internally unstable. Consider the following statements. The structure is unstable, correct. Bending moment is 0 at supports and internal hinge. Bending moment is 0 at support and internal hinge, correct. It is a mechanism, also correct. It is statically indeterminate. Statically indeterminate is wrong. It is unstable. 1, 2, 3 are correct. Which of the above statements are correct means B. So I told you mechanism, unstable. Both mean the same. And bending moment is 0 at 3 points is also correct. But statically indeterminate means is not correct. It's unstable. All the reactions we cannot say. Which of the statements are correct means statically indeterminate means the number of unknown reactions must be more than the equations of equilibrium available. In this case, static indeterminacy is negative. So, if ds becomes negative, we cannot say indeterminate. It is unstable. ds is equal to r minus s, 3 minus 4. You will get minus 1. Minus 1 implies unstable, not statically indeterminate. Like that. Okay, so 23rd B is the answer. Next, 24. Simply supported beam shown in figure. Like this, a beam is given. Two roller supports are there. That means it is a statically unstable structure. A load W is given. This is theta. Insufficient number of reactions are there. So it is statically unstable. If minimum 3 reactions are there but still unstable, we call it as geometrically unstable. But can we find the vertical reactions or not? We can find the reactions. So it is determinate and stable. It is not stable. Determinate and unstable. You can find the two reactions because W sine theta is shared by the two members. Sigma y0, sigma m0 we can find. We can use and find the two reactions. But because of the x component, W cos theta, it is moving. It is moving, but vertical reactions we can find. Okay. So it is determinate and stable. Determinate and unstable. Determinate and unstable. So VA, VB you can find. So more specifically, statically unstable. Third reaction is missing. Since two vertical reactions can be found, it is determinate. You can determine the reactions because vertical reactions you can find, but horizontal reaction there is no support at all. So it will translate, rigid body translation. So mechanism we call it. Okay. So as per the options, it is determinate and unstable. Next. Next, 25th question. Rigid plane frame ABCD has to be analyzed by slope deflection method. If it has to be analyzed by slope deflection method, all axial deformations are neglected. Slope deflection method. Axial deformations are neglected. So all members are inextensible case only they are. What is the number of unknown displacements or rotations for the frame shown in figure given below? So it is like this. This point, let us say A, B, C, D. There are some loads W1, W2, I1, I2, I3, whatever conditions they have given. Now here first you calculate dk when extensible. Dk here it is 0, here dk is 3, one floor level, here dk is 3, x, y rotation, here dk is 2, x displacement and rotation. So 3 plus 3, 6 plus 2, 8. Now dk when inextensible. Dk when extensible minus number of axially rigid members or number of independent displacements prevented, means each member in its longitudinal direction displacement is not possible. Because of that, axially rigid members means there are 3 you can cut them. So 8 minus 3, 5 degrees. Okay, so you have the answer as 5. 25th question, C. Next, 26th question. This 26th we have solved in the class. This one, 3 links and loaded as shown in figure. So you have to answer it as stable and indeterminate. It is stable for vertical loading only. For the given loading, we have to calculate stability or ds or dk if given. Since vertical loading P is given, vertical loading only you have to assume. There are 3 link reactions, so 3 unknown reactions, 2 equations of equilibrium. So ds is 1, but so stable also, because vertically downward loading it can take it. So stable and indeterminate to 1 degree. I have given you in the class stable and indeterminate to 1 degree. Solved in the class notes. Okay, 26 over. Next, 27. This also I have given you, but we'll see. Portal frame is there, has clamp support at A, hinge supports at G and H, axial force release. That means it is axial thrust release. We can call it as horizontal sleeve, horizontal force release, or axial thrust release. All mean the same. And moment release means hinge. Static indeterminates ds and dk you have to find. So this problem also we have solved, but with different conditions. So we will see that. This is called axial thrust release. Here there is a hinge. Right? So static indeterminate, this is you have to make a cut here. How many cuts are required? This they have given A, B, C, D, E, F, G, H. Number of cuts are here 1, 2. 2 cuts are sufficient. So ds is 3 into 2 minus number of reactions. I told you here you have to add one horizontal reaction, here one moment reaction, here one moment reaction, here one moment reaction. So minus 4. So 6 minus 4, 2 degrees. So ds is 2 degrees here. So only one option is there, directly C we can answer. If you want to find a dk, he has given how much? 19. Let us calculate what is dk, whether that matches or not. Here dk is 0, here dk is 3, dk is 4, dk is 3, 4, moment release 3, here dk is 1, here also dk is 1. Now count them, 3, 4 plus 3, 7 plus 3, 10, 14, 17, 18, 19. So dk is 19 degrees. First 19 degrees you have to search. If not there, 7 members I told you how to subtract. 1, 2, 3, 4, 5, 6, 7. So 2, 12 if it is given, say, then we will answer 12. dk when extensible. (19 minus 7, 12). This is inextensible. This is what I told you in the class, but he has given extensible case. So this is about the 27th problem. Now 28th question. Already this also we have solved in the class. Kinematic indeterminacy is 3. This we are taking inextensible case means it is 3. Then 29th also we solved in the class. It is a truss undergoing rigid body translation under arbitrary load. So we take it as statically unstable structure. Now neglecting axial deformation, dk we want to find. This is different. Hinge was there. Here it is, hinge. This is guided roller. Okay, this is the problem. Now he is asking you only to find the dk. Here dk is 0, dk is 3, here dk is 1, 3, here also dk is 3, 3, here also 3, here dk is only 1, here dk is 2. Now you will find that 3, 4, 7, 10, 13, 16, 19, 21, 24, 25. dk is equal to 25 when extensible. So, but 25 is not there. Now dk when inextensible, 25 minus number of axially rigid members. No bracing is done, so axially rigid members you subtract, minus number of axially rigid members. How many are there? 1, 2, 3, 4, 5, 6. Then 7, 8, 9, 10, 11. So 25 minus 11, 14 degrees. So dk is 14. That means B is the option. 30th is B. First we will see this one. He didn't mention whether he is asking you neglecting axial deformation. First we will find when extensible, then subtract number of axially rigid members. So quickly we can make it. Next, 31. Consider the following statements. A properly constrained means properly held rigid system has several degrees of freedom. That is one thing. Properly constrained rigid system has several degrees of freedom is wrong. Very less degrees of freedom will be there. The number of, so first statement is wrong. That means A and D are gone. The number of degrees of freedom of a locomotive moving on a railway track is only 2. So second one is wrong. Moving on a railway track, locomotive moving on a railway track, dk is only 1. So gone. So third one, a floating ship has 6 degrees of freedom. So 3 is correct. So 3 only is correct. So 31B. A properly constrained rigid system means everywhere fixity is there. It is a rigid system means very little degrees of freedom will be there. At the most sway will be there. That's all. Okay. Next 32 we solved in the class. It is those inclined members, we call them as knee bracing. So though he has given the pins as if they are kept at on the member itself, it is not connected to the member. Those dots must be away. It is like this. This is the correct diagram. It's a printing mistake. Because knee braces are made like this. So 3 cuts are there. 3 means 3 into 3. 9 minus 4, 5. dk you get 5 degrees. We have solved in the class. Degree of static indeterminacy. This is ds we have calculated. How? 3 cuts are there? 1, 2, 3 cuts. 3 into 3, 9 minus 4. So ds is 5 degrees. So 32C. This we have solved in the class. I have written what these are called. Knee braces. What is the purpose of knee braces? To reduce the bending moment and the deflection in the long beam. Or what if it all is a truss, small truss like that is provided, those braces will reduce the bending moment and deflection. Okay. Next 33. Kinematic indeterminacy of the plane frame shown in figure, disregarding the axial deformations. So neglect the axial deformations is the question. This is the hinge support, rigid joint, like this, hinge support. There is a hinge here. For this loading only you have to calculate. W1, W2 is there, say. Since loading is given, calculate dk for given loading system only. So when you are calculating the dk, now you see the deflection profile, how axial deformations are neglected. Now this behaves like a link. This point, let us say A, B, C, D. B will go to some B dash. C will go to some C dash. So BB dash, let us say delta. delta B, and delta C must be same. It is a link, so it will not rotate, it will not bend. It is a link because that member is not loaded at intermediate location and connected by smooth pins at the ends. So it will not bend, but it can rotate. Assume that this angle, say theta. Then here also it has no choice, theta, theta d, let us say. Then theta d is also, suppose length is L, say. Theta d is C dash by L. So not unknown. So this is also theta d. So you should not count. This also we should not count because delta C is delta B. So delta C is not unknown. But here it can rotate. It sways and bends and rotates. Assume that it has, when it rotates, it will hog. So something like that movement developed, let us say. There is some rotation here. So this also rotates. Okay. To maintain 90 degrees angle need not be maintained. So here there is a rotate. Fixed support, it's not a fixed support. So it will sag. Like this, say. So theta A will be there. Theta B different. If this is theta B, this is also theta B. Theta C is independent of theta D. Theta D, supposing that if you write theta C2 is nothing but theta D. This you take, say, theta C1. So number of unknowns are dk is equal to how much? Theta A, 1 here, delta B and theta B, independently it will come. Then delta C known to us, theta C1 known to us independent, theta C2 we can find, theta C2 is nothing but theta D is nothing but, that's all. So all other things we know. So dk is 4 degrees. 4 degrees, what they are also, if they ask, we can find. Or theta A, theta B, delta B, delta B and theta C. Say theta C1, more precisely if you want. So you will get dk as 4 degrees. So he has given 4, okay. 33D. But otherwise, if at all loading is here also, let us say, supposing that on the link also loading is there, theta D, these two slopes are also independent. Two slopes you have to add. But maybe the delta P is equal to delta C will be there, but theta C2, theta D, they are independent once load is there. Now load is not there, it behaves like a link, it does not bend, it is a straight line. From this geometry of the triangle, I can find theta D if I know delta C. If this is theta D, this theta C2 is also theta D. Like that. So number of independent displacements are only 4. Next, 34. Now see 34. Consider the frame shown in figure. If the axial and shear deformations in different members are assumed to be negligible, he gives you that shear deformations are negligible. Whether he gives it or not, shear deformations anyhow you are neglecting. Shear deformations, as I told you in the design of steel structures, they will come into picture if you don't have a solid web. So, shear deformations we have always treated as negligible only. But he has specifically mentioned as if one more additional thing will go off. Anyhow, all the cases that we have discussed till now are the cases of shear deformation neglected. All. Then axial deformations are neglected, then inextensible if they are considered extensible. But undercurrent is all of them shear deformations are neglected. But here he has specifically mentioned, but has no again additional meaning into that. Neglected. The reduction in the degree of kinematic indeterminacy. How much is the kinematic indeterminacy reduces because of your inextensible nature? How many members are there? How many axially rigid members are there? You see, vertically 4, horizontally 2. So number of axially rigid members are 6. So 6 will reduce. That's all. 34 B is the option. This is the case decay when inextensible is nothing but decay when extensible minus number of axially rigid members. Axially rigid members are 6. Because of your inextensible nature, he says decay how much reduces? Decay reduces by an amount of number of axially rigid members and they are 6. And he has given B as 6. Next, 35. Degree of static indeterminacy of a rigidly jointed frame in horizontal plane, that means a grid. Okay, 3-dimensional structure he has given. So something like this. And it is fixed here. Fixed here. Subjected to vertical loads only. One vertical load here, one vertical load here, one vertical load here. Ends are clamped to rigid wall as shown in figure below. It's a plane frame like a C shape frame and fixed at both ends. Vertical loads are placed. Here, because of this vertical loading, how many reactions will develop? Only vertical loading is there. There is one vertical reaction, VA, and there is no horizontal load, no horizontal reaction, but moment will develop. Due to this load, there is one moment, and due to this load, there is a twisting moment. If I show two lines, this is a twisting moment at A. In this direction, if I show perpendicular to the direction of the member, moment at A. Due to this load, bending moment. Due to this load, twisting moment. That's all. Due to vertical downward load, vertical reaction. So, 3 reactions only will develop. X direction reaction 0. That means in this direction 0 reaction. Perpendicular direction also reaction is 0. Z direction reaction couple will not form. Here also same thing. VB. Along the longitudinal axis there is a twisting moment because this load will twist the member. This is TB. And due to this load it will bend. Bending moment will act perpendicular to the longitudinal axis of the member, that means MB. So number of unknown reactions are 6. Equations of equilibrium are 3. What are they? Sigma Y0, sigma M0, sigma T0. Sum of the twisting moments. Okay. So we can write ds is equal to R minus S, 6 minus 3, 3 degrees. So 3 we cannot find. Then here in this case sigma x0, sigma z0 useless. Okay. To be more precise, this is if you take x-axis, let us say. sigma m sigma t instead of writing. Supposing that if you take this as say x-axis, this is a y-axis, this is a z-axis. Okay, then we can write sigma x0 is useless. Sigma x is equal to 0, you will get 0 is equal to 0, useless. Sigma z is equal to 0, you will get 0 is equal to 0. Then summation of moments about A is applicable. This sigma m0 means is actually sigma m z is equal to 0. This is say sigma y is equal to 0. You will get one equation, sigma mz is equal to 0, second equation. This to be more precise, sigma z. Then Tm is sigma mx. Sigma mx is equal to 0. This is nothing but summation of twisting moment is 0. This is nothing but summation of bending moments must be 0. But more technically, this is the correct way of writing. Sigma y0, sigma mz0, sigma mx0. These three equations of equilibrium are available. All other things, if you write sigma my is equal to 0, moments of all force about y-axis. Y-axis, they will not get, you will not get any moment at all. Okay? So, you will get 0 is equal to 0. So, moment about y-axis to happen, force must act horizontally. Then only it will rotate about y-axis. Horizontal forces are not there. So, 3 degrees is the option. So, 35C is the correct one. Is there like a special frame if you visualize? Which equations of equilibrium become useless? So, 3 become useless, 3 are useful. Next, the kinematic indeterminacy of the structure. Decay. Hinge support. Here you have this one. Then 2 lines here. Okay. Now 3 here, 0 here, 3, 3. All 3 we can make it. Here only 1, here only 1. 3, 6, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 into 3, 27, 28, 29. So dk is equal to 29 degrees when extensible. But 29 is not there. So 29 minus number of axially rigid members. 3, 6, 9. 10, 11, 12, 13, 14, 15. So you will get 14 degrees. Number of axially rigid members are 15. Now 14 is there. 36A. First this, if matches fine, doesn't match, subtract. Axially rigid members you subtract. Next 37. What is the total degree of static indeterminacy? He is asking ds. So the frame is like this. It's fixed here. Here you have internal hinges, and there is one more like this. Now you see, we have internal hinges are given. So we have 4 supports. So 4 cantilevers. 4 supports, that means 4 cantilever frames. So this, if I want to separate, I will make a cut here and here. This I want to make a cantilever, one cut is sufficient. Now this is a cantilever. This I want to make it one cantilever. This now looks like a cantilever. How many cuts are there? 1, 2, 3, 4 cuts only. So 4 cuts are there. Now see here 4 cantilevers we get it. Here -1, -1. This point let us say A, B. Static indeterminacy is 3 into 4 -1 at A -1 at B. 12 minus 2, 10 degrees. So 37, 10 degrees means 37 is A. Next 38. A planar truss they have given. There are 2 counter bracing members, into members, and both of them are supports are hinges. So hinge 4 reactions are there, that means 1 reaction extra. 2 counter bracing members. So external indeterminacy, if I take it, DSE R minus S, that means 4 minus 3, 1. DSI is 2 because two counter bracing members are there. So by seeing that, this what we get it. Now let us see what are the statements. P externally determinate, wrong. External static indeterminacy, 1, correct. So Q statement is correct. Then external static indeterminacy, wrong. So R is wrong. S is internally determinate, wrong. Internal static indeterminacy, 1 is wrong. Internal static indeterminacy is 2, correct. So U is also correct. Q is also correct. Which one of the following options is correct? Q, U are correct. Q, P, Q, U are correct, all are false. So option A. Q correct, U correct. That means all others are false. That means option A is the correct one. Because that into is there means 1 counter bracing. Bottom frame into is there, 1 counter bracing. Then 4 reactions are there, that means DSE is 1. 4 minus 3 is 1. Okay. So this is about the static and kinematic indeterminacy, to some extent stability of structures. What if you had listened to the classes carefully, static, kinematic indeterminacy and stability of structures, all these 35 questions or 38 questions you could have answered. Nothing new we have learnt. So that's why I told you read the class notes thoroughly. Then you should attempt on your own. That's why this we have taken in the end. Then you will know whether your understanding is proper or not. Now let us see the second chapter.